Problem 1 from the sample test involves something that you're going to be doing at the beginning of one of your problems in Calculus 2. It involves trigonometric substitution, where instead of looking at something like this, where you have a square root and something complex on the inside, I hope to be able to write it without the square root by using one of my Pythagorean identities. In this case, I'm going to spend most of my time working over here and only later work on this side. If I let x equal 3 sine theta, then x squared is going to be 9 times sine squared theta. 9 minus x squared would be 9 minus 9 sine squared theta, which would be 9 times 1 minus sine squared theta. And this is the important point. At some time, you have to use one of your Pythagorean identities. I know that sine squared plus cosine squared is equal to 1, so 1 minus sine squared is cosine squared. So this is 9 times the cosine squared of theta. That means that the square root of 9 minus x squared will equal 3 times the cosine of theta. Actually, it should have been the absolute value of the cosine of theta, but if you look at where this is going to be defined, this is going to be defined on values of theta between pi over 2 and minus pi over 2. For those values, cosine is positive. Finally, I'm able to go back to my original. Notice that I have an x on the top. I'm going to replace x with 3 sine theta. I have the square root of 9 minus x squared on the bottom. I'm going to replace that with 3 times the cosine of theta. The 3's are going to cancel. Sine theta over cosine theta is tangent of theta. And I am done. Here, I use a 1 minus sine squared to get a cosine squared. This is based off of sine squared theta plus cosine squared theta is equal to 1. You might also be called upon to use another Pythagorean identity, namely that tangent squared theta plus 1 is equal to secant squared theta. But on this problem, the key is that at some point I am going to have something that involves two terms condense by a Pythagorean identity to something that contains a single term. And now here I have a perfect square, so I can take the square root of it, and so I have a simplified version that does not include a square root. Very useful in Cal 2.